Hello viewers, welcome to my channel JEE Olympiads and AP Physics with Ambarish. And today once again I've brought a topic which troubles most of the students because it's not presented properly in NCERT. The derivation is not given and the phase relationship, even the formula is not given, but I've seen many test series questions on phase relations and a deeper understanding of forced oscillations. So that's why I've decided to bring this one shot on forced oscillations for all of you. This is one stop solution and all your troubles will be finished if you understand this video properly. So stay tuned till end and I'm sure you'll be able to master this topic very well for JEE main for this year, and as you might be knowing, next year it's very much part of JEE Advanced, and detailed theory is not given in most of the JEE literature. So this is going to be a very important video for especially JEE 2023 advanced aspirants, because this is not there in most of the standard JEE texts. So without much ado, let me straight away get into the problem, and then I'll also be telling all the detailed theory. First I'll state a problem to motivate you to understand the required theory, and then I'll start deriving the required theory. So here we go. Here is a problem that we intend to solve, and then we'll see how we will be able to solve it after deriving all the relevant theory. So what's the problem? Three similar oscillators A, B and C have the same small damping constant C. See, this is a damper and this is a mass and this is a spring, and damper means it applies a force proportional to velocity. So if it is moving with velocity x dot over here, so then it will provide a resisting force C x dot. X dot means derivative of x with respect to time, which is velocity. Okay. So we have three similar oscillators A, B and C which have the same small damping constant C. So damping constant is small and it's given by the symbol C. Normally NCERT uses the symbol B for it, but most engineering textbooks they use the symbol C. So I have stuck to the popular convention. So they have same small damping constant but different natural frequencies. Natural frequency means under root of k by m, where k is the spring constant, m is the mass of the slider, and they have the frequencies respectively 12 Hz, 1800 Hz and 2400 Hz respectively. If all the three are driven by the same source as at 1800 Hz, which statement is correct for the phases of the velocities of the three? So these are the four options, and now how to solve this? Obviously you need to understand theory for solving this, and let me now get into the theory. Okay, so let's see the differential equation. So if you consider the free body diagram of this mass, suppose its displacement from the mean position is x, and let's say its velocity is x dot in this direction. So cx dot, this is the force due to the damping, and then there is a kx force due to the spring. And now I can write, and of course there's a forcing function given by f naught sine omega t, and now I can write the differential equation f equal to ma force. So what is that? So rightward direction I have taken as positive, so leftward forces are negative. So minus kx and minus cx dot plus f naught sine omega t, that should be equal to mx double dot, that's mass times acceleration. And if you rearrange this equation, you simply get mx double dot plus cx dot plus kx is equal to f naught sine omega t. So this is the standard differential equation for forced oscillations, and now we want to find out its solution. So it turns out that when you switch on the system, initial response is a bit complicated. It contains some exponentially decaying terms with time. However, when you give sufficient time for the system to settle, then in steady state the system is undergoing only sinusoidal oscillations, and the angular frequency of the sinusoidal oscillations is same as the angular frequency of the driving force, that is same omega. X will have same omega as the driving force. Okay, so we are not interested in the transient solution, the initial unsteady state. We are interested in the steady state solution for our JEE purposes. Okay, so now how to solve for steady state? So what I've written, initial response to the equation 1 when the system is just started is complicated and has some exponentially decaying terms with time. However, in steady state the displacement varies sinusoidally with the same angular frequency as the driving force. So now let the solution to equation 1 be of the form x is equal to a sine omega t minus phi, where a is some amplitude and phi is some phase lag here. Phi is the angle by which displacement lags behind the forcing function. So I have just assumed, and now if I find A and phi, my job is done. Okay. So now I substitute the RHS A sin omega t in the LHS of equation 1. So if you put x as A sin omega t, so this is x is A sin omega t, so x dot becomes A omega cos omega t, and cos omega t minus phi. So this is A sin omega t minus phi, this becomes A omega cos omega t minus phi, and this will then become minus A omega square sin omega t minus phi. So that's what I've done. So minus A omega square sin omega t minus phi, and m was already there. Then A omega cos omega t minus phi, and c was already there, and ak sin omega t minus phi. So A sin omega t minus phi and k was already there. Okay, and this is equal to f naught sin omega t. Now what do we do? Now since equation 3 holds at all times, once the steady state is established, I start my clock in the steady state itself, you can say. And then once my clock is started in the steady state, I can use this at all times. So how to solve this equation? So two unknowns A and phi can be obtained by setting omega t is equal to minus phi is equal to 0 and omega t minus phi is equal to pi by 2. We choose two particular times for study. Now why this is going to work? See, if I choose omega t minus phi equal to 0, then sin omega t minus phi terms will become 0. And of course then if omega t minus phi is 0, then omega t becomes phi. So right hand side will become f naught sin phi, and these two terms will vanish. Okay, so what do I get if I put omega t minus phi equal to 0 in equation 3? So this equation reduces to, this goes to 0, sin omega t minus phi, this goes to 0, you are left with AC omega, and cos 0 becomes 1. So AC omega is the LHS, and right hand side becomes simply f naught sin phi. Why? Because omega t becomes phi if omega t minus phi is 0. So this is one equation in A and phi. What about the other equation? So I can also say that this equation is also valid when omega t minus phi is pi by 2. So another convenient time. Okay. So if omega t minus phi is pi by 2, then omega t becomes pi by 2 plus phi. So omega t becomes pi by 2 plus phi. So right hand side will become cos of phi, right? And what happens to the left hand side? See, so if omega t minus phi is pi by 2, then this term cos omega t minus phi will be 0, right? And I'll be having only these two terms, and they'll also be simplified. So what will I be left with? So if omega t minus phi is pi by 2, the sine terms become 1, and this cos term becomes 0, and this becomes cos phi. So what do we get? We get minus am omega square plus ka is equal to f naught cos phi. So I hope you understood equation 5. It's simple substitution. Sin omega t, omega t minus phi I have put as 1 because omega t minus phi is pi by 2. So I hope you understood equation 5 also. And now in equation 5 and equation 4 you have two unknowns A and phi. And of course now you can find A by using that sin square phi plus cos square phi is 1, and tan phi you can find by dividing sin phi and cos phi. Okay, so let's see what do we get. So now using sin square phi plus cos square phi equal to 1, we get this sin phi is AC omega by f naught, so that's what I have written, and cos phi is minus am omega square plus k upon f naught, so that's what I have written. In fact you can take a common, then it becomes k minus m omega square by f naught whole square is equal to 1. And if you solve this, then you get a is equal to f naught upon under root of k minus m omega square whole square plus c square omega square. So we have already found the amplitude, and this is equivalent to the result given in NCRT. If you really want to write this equation in NCRT equivalent form, you can just rearrange this. What you can do, you can take m square common outside, and then inside then you'll have to put k by m. And what is k by m? K by m is nothing but square of the natural frequency, right? So what do we mean by natural frequency? If there were no damping and there were no forcing, then you know that the system would oscillate by a frequency root of k by m, natural frequency. Okay, so then k by m becomes nothing but omega natural squared, right? So you can take m square common outside, and instead of k by m, this becomes omega natural square, and this becomes omega square, and c square omega square comes as it is. So this is the equivalent form. You might like to memorize this because this is the form that's given in NCRT, except for instead of c they have written the symbol b, and instead of omega, NCRT somehow uses omega d for the driver omega, and omega naturally represent by omega. So don't worry, you can, this is I believe a better way of writing the same thing. So you can memorize this formula and this is how you derive it. Okay. Okay, here omega n is the natural frequency, and this can also be written in another form that most engineering textbooks use. They write using what is known as damping ratio. And what is damping ratio? Damping ratio is C upon 2 root mk. So if you use that, you can easily show that this equation is equivalent to equation number 8. So what you will do, you can make whole thing dimensionless by dividing by m square and omega n square, and then somehow you will get this damping ratio. You can prove that equation 8 is equivalent to equation 7. Okay, so this becomes f naught by k divided by 1 minus omega upon omega n squared whole square plus 2 zeta omega by omega n whole square, where zeta is C upon 2 root mk. Okay, so sometimes this form is useful, although it's a bit hard to memorize. No need to memorize this, but just for information I've written. I'll also be showing a plot of this one later on. Okay, and sometimes it's convenient to define a dimensionless ratio m is equal to a upon f naught k. See, this f naught by k must have same dimensions as a, so you can take this f naught by k over here, and a upon f naught by k is called magnification factor. So that's a dimensionless measure of amplitude, you can say, or you can say relative amplitude. How the amplitude, relative amplitude varies with the driver frequency omega, so that we can study. So if you do that, the equation 8 can be rearranged in this form. So m is a upon f naught k here. Okay, so this is your magnification factor with varying with omega, driver frequency. Here omega n is the natural frequency, and zeta, as I told you, is C upon 2 root mk. It's also called the damping ratio. Now what's the physical significance of zeta? It turns out that this terminology zeta is coming from the topic of damped oscillation. So it happens that if zeta is less than 1, then we have damped oscillations, and if zeta is 1 or more than 1, then we do not have an oscillatory solution. So that's the physical significance of zeta. Okay, now we can also find the phase angle using the fact that tan phi is sin phi upon cos phi, and if you do that, you get phi as tan inverse of C omega upon k minus m omega square. You see equations 4 and 5. So from here you get sin phi, and from here you get cos phi, and you divide the 2, and a will cancel off, and you will be left with C omega divided by k minus m omega square. So that's what I've written. So tan phi is C omega upon k minus m omega square, or phi is tan inverse of C omega upon k minus m omega square. But a word of caution here, even though I've written here tan inverse function, you should consider the principal range of tan inverse from 0 to pi. Although the principal range is considered as minus pi by 2 to plus pi by 2, but here bear in mind, here you have to use from 0 to pi. It can be rigorously shown using complex numbers that here tan inverse of a small negative number you will have to put as pi, and and not 0 here. Okay, so you can consider it as a modification to the standard theory in maths. Here, if you are writing in the form of tan inverse, assume the principal range to be 0 to pi. A more rigorous derivation can be done using complex numbers, which I have avoided deliberately, but just keep this in mind so that you don't make a mistake. Okay, and later on we'll be using this. So principal range will be using for tan inverse as 0 to pi. Okay, and the same thing in Marian-Craig notation, you can write it like this. Again, zeta is C upon 2 root mk, the damping ratio. Okay, so sometimes it's useful to write it this way. Okay, now there are some important points. So first important point is we can ask that at what driver frequency is the amplitude of oscillations maximum. So we have the function for amplitude. This is the function for amplitude. So you know that for maximum amplitude the denominator should be minimum, or the quantity within the square root should be minimum. So what you can do, you can differentiate the quantity within the square root with respect to omega and put it equal to 0 to maximize the amplitude. So that's what if you do, what you will get. So we can minimize the denominator of equation 6 with respect to omega, that is d by d omega of k minus m omega square whole square plus c square omega square equal to 0. And if you do that, you do a little algebra, what you will get, if you solve for omega, you get maximum omega comes at under root of k by m minus c square by 2m square. Now this is important. See, if the damping is very very small, then omega max is simply root k by m. But if the damping is significantly large, then you cannot ignore this term. C square by 2m square must be considered. So when is it large or small? That depends on whether, again, zeta is much less than 1 or not. So zeta is c upon 2 root mk, and if this quantity is very less as compared to 1, then you can ignore this. But otherwise, bear in mind that maximum amplitude does not occur at under root k by m. It definitely occurs at a frequency less than root k by m, although it can be very close to root k by m if c is very small, or you can say c upon 2 root mk is much less than 1. Then you can simply write root k by m. Sometimes students get a misconception after reading NCERT. They think that root k by m itself is the frequency for maximum amplitude. That's not true. Okay. For small damping, although, omega max becomes same as natural frequency, that is under root k by m, right? Now we can also conclude certain things about phase from equation 11. So let's see the equation 11 carefully. You see what happens if omega is very small. If the driving frequency is very small, then the numerator goes to 0. Okay, if omega is 0, then numerator goes to 0, and then tan phi is 0. And if tan phi is 0, of course phi is 0. That means what? At very small driving frequencies, the displacement will be in the same phase as the forcing function. So if omega is almost 0, then displacement is almost in phase with the forcing frequency. There is no phase lag almost. Okay. And when omega is equal to natural frequency, again we can see in the equation 11. See, if omega is equal to natural frequency, omega and omega n are equal, then this term goes to 1 and denominator then goes to 0, and then tan phi goes to infinity. That means what? Phi goes to pi by 2. Okay, so that's what I've written. When the driving frequency is same as the natural frequency, phi is pi by 2, or we can say displacement lags behind the forcing function by a phase of pi by 2. Okay. Then the third case is when omega is very large as compared to natural frequency, then tan phi is a very small negative number. Okay. So again, equation 11, if you see, if omega is very large, what happens? If omega is very large, then this is 1 minus a very large number in the denominator, and therefore this becomes a very small negative number. So tan phi is a very small negative number, means what? Phi is pi. Okay, if we consider the principal range. Okay, so if the driving frequency is very large, then the force and the displacement are exactly out of phase. So that's what I've written. Okay, so tan phi is a very small negative number, and the displacement lags behind the forcing function by pi, or we can say displacement and force are exactly out of phase. That means if the force is to the right, displacement is to the left, and the other way around, right? And also, when omega is less than natural frequency, then phase lag lies somewhere between 0 and pi by 2. We saw that when omega is 0, phase is 0. When omega is omega n, phase is pi by 2. So that means what? If the driving frequency is somewhere between 0 and natural frequency, the phase lag is somewhere between 0 and pi by 2. Okay. And when driving frequency is more than the natural frequency, then the phase lag will lie between pi by 2 and pi. Why? Once again, at natural frequency the phase lag is pi by 2, and at infinity the phase lag is pi. So if the driving frequency is somewhere between natural frequency and infinity, the phase lag is somewhere between pi by 2 and pi, and that means for very large frequencies it is about pi. The displacement lags behind the force by a phase of pi. Okay. Now we can also look at the plots showing the variation of magnification factor and phase angle with the ratio omega by omega n. Recall that magnification is nothing but a measure of amplitude, and we have just made the quantity dimensionless by dividing amplitude by f naught by k. So if you do that, if you look at the plot, magnification force versus relative frequency, so one thing you can see is that so when zeta is 0, that is there is no damping, you can see that maximum amplitude occurs at omega equal to omega n, or omega by omega n equal to 1. You can see the peak will be here. But when there is some damping, you can see this peak is shifting to the left, right? For example, when zeta is 0.5, that is c by 2 root mk is about 0.5, you can see peak is somewhere over here. Okay, so as I told you that maximum amplitude need not occur at natural frequency, it will occur at slightly lesser frequency than the natural frequency if there is some damping. For example, this peak also, if you see, it's very close to the quantity omega by omega n being 1, but it is slightly to the left. Okay, so this is our graph of magnification factor, that is kind of amplitude dimensionless, made dimensionless with respect to relative frequency, that is omega divided by natural frequency. So I hope you understood this graph. And now we can also plot the graph of phase lag versus relative driver frequency. So whatever we got for tan phi, the same thing we have shown here in the form of plot. Okay, so when there is no damping at all, when zeta is 0, that means c by 2 root k, mk is 0, or c must be 0, then our phase lag graph is simply like this. So it is a straight line, then vertically up, and then straight line. That means in case of no damping, the displacement and forcing function will be either in same phase or exactly out of phase. There's nothing in between, right? So till the driving frequency is less than the natural frequency, the forcing function and the displacement function, they are in the same phase. Okay, and when the driving frequency is more than the natural frequency, the forcing function and the displacement function are exactly pi out of phase, right? So there's a phase lag of pi. And what happens at other frequencies or other if the zeta or the damping is there, finite damping is there. So you can see for zeta is equal to 0.1, this S-shaped graph is there. For zeta is equal to 0.2 and 0. So you can see this type of a graph happens, and that means what? So here the same thing you can see. If driving frequency is somewhere between 0 and natural frequency, the phase lag is somewhere between 0 and pi by 2, right? And when the driving frequency is more than the natural frequency, you can see phase lag is somewhere between pi by 2 and pi. Okay, so here it is between 0 and pi by 2, and here it is between pi by 2 and pi. And of course at very large frequencies, all these graphs will be saturating to pi. Okay, so that's the graph of phase lag versus relative driver frequency. I hope you understood this concept also. And now coming to the challenge problem. Okay, so what was our problem? Three similar oscillators were there, ABC, having same small damping coefficient C, constant C, but different natural frequencies, omega naught, which is root k by m, 1200 Hz, 1800 Hz and 2400 Hz respectively. If all the three are driven by the same sources at 1800 Hz, which statement is correct for the phases of velocities of the three? So now you see the driver frequency is 1800 Hz, while for the first one, the natural frequency is 1200 Hz. That means what? For oscillator A, the driving frequency is more than the natural frequency, right? So when the driver frequency is more than the natural frequency, what happens? See, so for oscillator A, driver frequency 1800 Hz, natural frequency 1200 Hz. So omega is greater than the natural frequency. That means lag of displacement phase between pi by 2 and pi. Okay, so driver frequency more than natural frequency, that means the phase lag will be somewhere between pi by 2 and pi, as I just now showed you in the graph. And therefore what will happen? So but velocity leads displacement by a phase of pi by 2. Here remember, we don't have to comment on the phases of displacement, but we have to comment on phases of the velocities of the three, right? So what happens to the velocity phase? So velocity leads displacement by a phase of pi by 2, because you see, if x is a sin omega t, then v is nothing but a omega cos omega t, which is sin omega t plus pi by 2. So whatever is the phase of displacement, we just need to add a pi by 2 to the phase of displacement to get the phase of velocity. So since displacement is somewhere between minus pi by 2 and minus pi, because it's a lag there, therefore it should be considered as minus pi by 2 and minus pi as far as phase is concerned, right? So for velocity, if it is minus pi by 2, you add another pi by 2. So minus pi by 2 plus pi by 2. So velocity phase of A must be a number between minus pi by 2 plus pi by 2, that is this one, and minus pi plus pi by 2. So that is phase of A must lie somewhere between, velocity phase must be somewhere between minus pi by 2 and 0. Okay, so that is for oscillator A. Now for oscillator B, omega is same as natural frequency. Both are 1800 Hz. See, the driver is also 1800 Hz and the driven is also 1800 Hz for oscillator B. That means what? Displacement lags behind by a phase of pi by 2 behind the forcing function. So displacement lags behind the force by pi by 2. So velocity phase is what? So since this is a lag of pi by 2, so phase is minus pi by 2. So minus pi by 2 plus pi by 2 becomes 0. So phase of velocity of B is then 0. Okay. And for oscillator C, so oscillator C, omega is less than the natural frequency. You see, driving frequency is 1800 hertz, and the driven frequency is, the natural frequency of the driven is 24 hertz, whereas driving frequency is 1800 hertz, right? So we can say that omega is less than the natural frequency now. So that means what? This time displacement phase lag will be somewhere between 0 and pi by 2. So velocity phase will be a number between 0 plus pi by 2 and minus pi by 2 plus pi by 2. That is, velocity phase is somewhere between 0 and pi by 2, right? This becomes pi by 2 and this becomes 0. So velocity phase must be somewhere between 0 and pi by 2, right? So these three are the facts. So for A, phase is between minus pi by 2 and 0. For B, the phase is 0. Okay. And for C, the phase is between 0 and pi by 2. So combining these three, we can get phi A is less than phi B, which is equal to 0, and this is less than phi C. So we get option B. So that was my analysis for forced oscillations with damping. And I am sure if you have seen this video carefully, all your doubts will be cleared about forced oscillations, and you will be able to do almost every problem, not almost every problem on forced oscillations based on this differential equation nicely. And I hope that this analysis was useful for you. If you found this video useful, please do give it a thumbs up, and please share this video as much as possible with your friends who are preparing for JEE through WhatsApp, Telegram, Discord, or whatever medium you might be using for networking with them. And most importantly, if you have not already subscribed to my channel, please do subscribe to my channel right away, because that's what keeps me motivated to do a new video almost every day. Thanks a lot for watching this video, and I'll see you in the next one. And as always, God bless you all. Thank you.